A very good morning to all of you. We are discussing magnetic dipoles, and let me recall, in the last lecture we had looked at torques and energy of a magnetic dipole. So, we had defined a magnetic dipole by considering a loop of wire carrying a current I and of radius r. So, the magnetic moment, so magnetic dipole having a magnetic moment m is equal to I times A area vector. In this case, the current is propagating like this. So, the area vector is pointing up and the magnetic dipole moment is pointing up. We also calculated the magnetic field due to a dipole, and we had done this for field along axis B is equal to mu naught m by 2 pi times z cube, where z is much greater than the radius of the coil. So, we are this magnetic field is on the axis far away from this dipole, and it has the same direction as the magnetic dipole moment. Similarly, we had done a calculation for field in the plane, and B was equal to minus mu naught m by 4 pi x cube, where x much greater than r. So, this is, we had assumed this is a z direction, this is x direction, and so far away from the dipole, the magnetic dipole field along the axis is mu naught m by 2 pi z cube. It is parallel to the magnetic field, it is parallel to the magnetic dipole moment, and the field in the plane is minus mu naught m by 4 pi x cube. So, if I were to draw a figure here, if this is the dipole m, then this is the axis of the dipole and this is the plane perpendicular to the dipole. So, here the magnetic field is like this, here the magnetic field is like this, B is parallel to m, and here the magnetic field is downward, here the magnetic field is downward. So, B in the plane is minus of m and B in the axis is along the m direction. So, we had obtained these magnetic fields of a dipole far away from the dipole, and also we had calculated the torque on a dipole due to an external magnetic field B as tau is equal to m cross B. So, the torque is m cross B, and the torque on the dipole tends to align the dipole along with the magnetic field. So, the torque tries to align the magnetic dipole along the direction of the magnetic field. We had also calculated the potential energy of the dipole in an external field u is equal to minus m dot B. That is the potential energy, and the zero of the potential energy is assumed to be when m and B are perpendicular to each other, and the external field tends to align the dipole parallel to the magnetic field, and where the potential energy is minimum and equal to minus mB. When m and B are parallel, the potential energy is minimum, that is minus mB, and when m and B are anti-parallel, the potential energy is maximum, and that is plus mB. So, as the dipole goes from anti-parallel to parallel, so if the magnetic field is pointing up and the magnetic dipole is pointing down, maximum potential energy and as it twists and comes in this direction parallel to the magnetic field, the potential energy is minimum when the dipole is oriented along the magnetic field. So, whenever you have a dipole, magnetic dipole, the external field tends to apply a torque on the dipole, tending to align the dipole along the magnetic field. We started looking at one example in the at the end of the last class, and that is, let me recall the example again. We have a loop carrying current I. Let me assume this is the x axis, this is z axis, and so the right handed system y axis is like this, y axis is going inwards. Let me also assume there is a magnetic field, uniform magnetic field in this direction. So, it is given that the radius of the coil is 5 centimeters, the current through the loop is 5 amperes, and the magnetic field, the external magnetic field B is equal to 0.1 Tesla and oriented along the x direction. So, I am given a loop carrying current, a loop of radius 5 centimeters carrying a current of 5 amperes and placed in an external magnetic field of strength 0.1 Tesla. So, first let us calculate the magnetic moment of this loop. Magnetic moment of this loop m is equal to I times A, and because the loop is carrying a current in this direction, with the right handed rule the area vector points along the z direction. So, this is equal to I into pi r square into k cap, and so we can substitute this. So, 5 amperes into pi into r square, which is 25 10 to the minus 4 k cap, and that is equal to 1.25 pi into 10 to the minus 2 k cap ampere meter square. So, the magnetic moment, dipole moment of this loop is 1.25 pi 10 to the minus 2 k cap ampere meter square. So, the moment, dipole moment is pointing upwards along the z axis, and this is now placed in a magnetic field pointed along the x direction. So, as we have seen before, the torque will be tau m cross b. So, m is pointing upwards, b is pointing this way. So, if you look at m cross b, the torque will be oriented along the y direction. So, we can calculate the torque on this loop. Torque on the loop, tau is equal to m cross b, which is equal to, we have just calculated m, 1.25 pi 10 to the minus 2 k cap cross 0.1 I cap. So, this is equal to 1.25 pi into 10 to the minus 3 j cap. K cap cross I cap is j cap, and as you can see there is a torque which is acting along the j cap direction. So, j cap is in this direction. So, the torque is tending to align the loop along the x axis, the area of the loop to be along the x axis. So, there is a torque acting on this loop which is tending to align this and along the, and the torque is oriented along the j cap direction. Now, I can also calculate the potential energy. Change. So, when change in potential energy, when the coil, when the loop goes from this position to a position which is minimizing the potential energy. So, the loop is like this now, it gets the torque will try to align this, and the loop will get aligned perpendicular to the x axis. So, initial potential energy now is equal to 0, because in this orientation m is along z axis, b is along x axis, and m dot b is 0. The final potential energy minus m dot b, which is equal to minus m b, where m becomes parallel to b, which is equal to minus 1.25 pi into 10 to the minus 3 joules. Now, the stock has a unit, Newton meter, and this is 1.25 pi minus 1.25 pi 10 to the minus 3 joules. That means, the potential energy decreases as the loop gets aligned along the direction of the magnetic field. And similarly, if you have to, I leave it a problem to you, what is the work to be done to align the dipole not from this orientation to this orientation. That means, the dipole moment pointing along the minus x cap direction. So, I must, as you will see, that whether I have to do work on the dipole or the field does not work on the dipole, you can calculate what is the work to be done in rotating the loop from this orientation to an orientation in which the magnetic dipole moment is pointing along the minus x cap direction. So, I leave this as a simple problem to you to calculate what is the energy required for the change in potential energy in this process. Now, we have done all this calculation for torques etc., to finally understand what happens to the magnetic field in the presence of matter. Now, in the case of electrostatics, remember we had discussed, initially we looked at electric fields in free space, and then we introduced the concept of dielectrics and said that when you place a dielectric inside in an electric field, the electric field polarizes the dielectric. That means, creates small electric dipoles within the material, and these small electric dipoles create their own electric field, and what you observe is the sum of the electric field that you have applied and the electric field that the dipoles are generating. So, in a similar fashion, we need to understand what will happen if I place a medium in a magnetic field. What is the effect of a magnetic field on the medium, and whether the medium affects the magnetic field inside the medium, outside the medium, etc. So, for this we must recall that all matter consists of atoms, and these atoms are actually made up of electrons and protons and neutrons, and in all these atoms the electrons are in the simplest picture revolving around the nucleus, and these orbital motions of electrons constitute a current. So, you have in the simplest picture, I can assume that I have a nucleus in which the electron is revolving, and this revolving electron has a constitutes a current in the system, and that current will have its own magnetic moment. And so, this magnetic moment will then try to generate a magnetic field outside. So, please remember that this current is different from a current that you will flow in a wire. If you have a wire, if you have a conducting wire carrying current, there are actually electrons flowing from one end of the wire to the other end. That is something called conduction current. So, electrons are actually flowing from one end to the other end. In an atom, the electrons are revolving within the atom itself, they are not freely flowing within the atom within the system, and these atomic currents also constitute dipoles, and these dipoles also create their own magnetic fields, and what you need to understand is the total magnetic field generated by the conduction current as well as the bound atomic currents. So, these currents, bound currents, do not actually get transported from one end to the other end, they are just circulating around each of the nuclei, but they still constitute currents. Now, in many materials these currents are producing magnetic dipoles which are randomly oriented, and so the material does not produce a magnetic field outside the material. There is no magnetic field generated because they are all randomly oriented. Now, because you can represent each magnetic dipole as a current which is flowing like this, and we can define, so we have magnetic dipoles, small dipoles, miniature dipoles, each atom represents a dipole, and so in the case, just like in the case of dielectric, we have introduced a concept called polarization. So, if you have take a medium, recall, if you take a medium and put it in an electric field, external electric field, the electric field generates small dipoles, each atom becomes a dipole, electric dipole, and we then define the total dipole moment per unit volume, electric dipole moment per unit volume, which we had called polarization. Similarly, we will introduce a new concept here which is called magnetization. Magnetization is the dipole moment. This is magnetization m vector. M vector is the dipole magnetic dipole moment per unit volume. So, you take a small element infinitesimal volume of the material. The small volume should contain thousands of atoms, and then you calculate the total magnetic moment of the small volume. So, I take a volume delta V, I sum up all the magnetic moments of all the constituting atoms to get the total magnetic moment. Please remember, magnetic moment is a vector. So, I must add all the magnetic vectors vectorially. So, I get the total magnetic moment of the small volume and find out the limit as the volume tends to 0. So, we will get a magnetization, and then magnetization implies that the material has a magnetic moment per unit volume, and a material which is which has this magnetic dipole moment is called magnetized. Magnetized medium. So, when you place a medium in an external magnetic field, the external magnetic field alters the magnetic structure of the atoms within the material and magnetizes the medium. Just like an external electric field polarizes a dielectric, which means creates electric dipoles within the material, a material placed in an external magnetic field also magnetizes the material, the medium, and the medium is said to be magnetized in the presence of an external magnetic field. So, we will consider a very simple model to understand the magnetic moment of atoms. This is the model which was proposed by Niels Bohr, and in 1911. An atomic model in which the proposal was, I have a nucleus and I have electrons revolving around the nucleus. So, please remember, to describe the atoms I need quantum mechanics, which is beyond the scope of this course here, but in a simple picture I can assume that the atom consists of a nucleus at the center, positively charged nucleus, and the electrons are revolving around the nucleus. So, this electron motion like this constitutes a current, and I can calculate what is this current, and once I have a current I can also calculate the magnetic dipole moment of this. So, let me assume this is an orbit is circular of radius r. So, and let me assume the velocity of the electron is equal to v. Radius of the orbit is equal to r. So, I have an electron circulating around the nucleus at a distance r from the nucleus, and let me assume that the orbit is circular. So, the time taken for one revolution of the electron t is equal to, so if the electron starts from here and goes one full circle, it has travelled a distance 2 pi r with a velocity v. So, the time taken is 2 pi r by v. So, the time taken for one revolution is 2 pi r by v. So, I can calculate the number of revolutions per unit time is equal to 1 by t, which is equal to v by 2 pi r. It takes a time t for one revolution. So, the number of revolutions per unit time is 1 by t, which is v by 2 pi r. So, that means if I am positioning myself at a point here, so many times the charge will cross B, and because the charge of the electron is E, this will constitute a current. So, I can calculate the current as the charge multiplied by the number of revolutions per second. So, the charge crosses this point, any point on the circle 1 by t times per second. Each time the charge crosses, the charge crossing is E. So, the current is essentially the charge crossing per unit time, which is E by t. So, this is nothing but E v by 2 pi r. So, that is the current, let me call it I. So, this electron orbiting around the nucleus constitutes a current given by E v by 2 pi r. Now, if you have a current in a loop like this, we know that this also constitutes a magnetic dipole. So, I can immediately calculate the dipole moment, magnetic dipole moment m is equal to current into area. I am calculating the magnitude of the dipole moment. So, at every point there is a current which is I, and the current has a it is a loop of radius r. So, the magnetic dipole moment is I times pi r square, and which is equal to E b by 2 pi r into pi r square, which is equal to E b r by 2. Pi cancels off and r cancels off E v r by 2. So, that is the magnetic dipole moment of the of this loop here. So, this dipole moment will then generate a magnetic field, and we have already seen what is the magnetic field generated by a dipole along the axis or in the plane perpendicular, and in principle you should be able to calculate the magnetic field generated by the dipole at all points. But so, this magnetic dipole will generate its own electric field, its own magnetic field, and I can relate this dipole moment to the angular momentum of the spinning electron. So, what is the angular momentum? L is equal to mass of the electron, which I call m e, into v times r. m v r is the angular momentum, that is equal to mass of the electron. So, m e is the mass of the electron here. Please note m is representing the dipole moment and m e represents the mass of the electron. So, I can use these two equations to write a relationship between dipole moment and angular momentum. So, m is equal to E by 2 m e times L. So, I have replaced V r by L by m e, and I get E by 2 m e into L. Now, magnetic dipole moment is a vector, angular momentum is a vector. So, let me convert this into a vector equation. So, now see here, the electron is spinning like this in this direction, and electron is a negatively charged particle. So, actually the current is going in this direction. So, when the current goes like this, dipole moment is pointing downward. A current constituted like this will constitute a magnetic dipole moment which is pointing downward, but the electron is spinning like this. So, the angular momentum is pointing upward. Please note, electron is spinning like this, so it has an angular momentum pointing upward. Electron spinning like this constitutes a current which is in this direction, in the opposite direction, and a current going like this will produce a magnetic dipole moment which is pointing downward, which means in this case the dipole moment and angular momentum are in opposite directions. So, in a vector form I can write m is equal to minus E by 2 m e times L vector. So, dipole moment and the angular momentum are related through this equation, and this equation we have obtained classically by looking at the atom to be consisting of electrons which are revolving around the nucleus, and I get a relationship connecting the dipole moment and the angular momentum. Now, I need to bring in a little bit of quantum mechanics here. It is found using quantum mechanical principles that angular momentum cannot have arbitrary values. Now, this is not obtained classically by this argument, but if I use quantum mechanics, I find that the angular momentum cannot have arbitrary values, but so according to quantum mechanics, L can have only can only be multiples of this quantity, which is equal to n h by 2 pi, and n is an integer. That means the angular momentum can only be integral multiples of this h cross, which is h by 2 pi, h is the Planck's constant, which is equal to approximately 6.626 10 to the minus 34 joule second. Now, this is a relationship from quantum mechanics, that the angular momentum of the electron can only be multiples of h cross, and that is n h cross. And so, I also find now here that if L has to be of the form this, I can write down the smallest value of magnetic dipole moment. So, fundamental unit of magnetic dipole moment m is equal to, so I had E by 2 m e into L, the smallest value of L is h by 2 pi. So, I will have L E by 2 m e into h by 2 pi, which gives me E h by 4 pi m e. Fundamental unit of magnetic dipole moment is E h by 4 pi m e. This is called the Bohr magneton. So, you can substitute. So, I can write the Bohr magneton as m b. You can substitute the electronic charge, the Planck's constant, and the mass of the electron, and you will find this approximately 9.274 into 10 to the minus 24 ampere meter square. So, what we find is the dipole moment is a multiple of this quantity, which is the fundamental unit of dipole moment. And so, I can associate with the orbital motion of the electron in an atom an orbital dipole moment, which is represented by the Bohr magneton. So, orbiting electrons which are orbiting around the nucleus have their own magnetic moment, which is also referred to as orbital magnetic moment. These are called orbital magnetic moment. Each of the circulating electrons within the atom has an orbital angular moment, and the total moment can be obtained by adding the vectorially the orbital magnetic moments of each of the individual atoms. Now, it is also found that apart from this magnetic moment, electrons also possess another very important quantity, which is called the spin angular moment. Spin magnetic moment. Now, spin is an intrinsic quantity, much like charge and mass of the particle, and associated with this spin is a magnetic moment, and the magnetic moment, spin magnetic moment, has a magnitude of almost 1 Bohr magnetron. So, in an atom you have electrons which are orbiting the nucleus. We associate a magnetic moment with the orbital motion called the orbital magnetic moment. Each of the electron is characterized by a spin, an intrinsic quantity called spin, and along with the spin we associate another magnetic moment called the spin magnetic moment. So, the total magnetic moment of the atom will actually be obtained by vectorially adding the orbital angular momentum of all the electrons and the spin angular momentum of all the electrons to get the total magnetic moment of the atom. So, it is these magnetic moments of the atom which constitute the dipole inside the material, and these dipoles may produce their own magnetic field. So, when you place a medium inside a magnetic field, we are actually modifying the magnetic property of the atoms, and that leads to and the medium itself, magnetic property of the medium, and that leads to a generation of a magnetic field by the medium, and what you observe total magnetic field is the sum of the applied magnetic field and the magnetic field generated by this magnetized medium. Now, I want to look at physical interpretation of this magnetization. So, what is the physical picture? Of a uniformly magnetized medium. Remember, in the case of electrostatics, we had a physical picture of what is the meaning of a uniformly polarized medium. We showed that a uniformly polarized medium is equivalent to generation of surface charges at the surfaces of the medium, and those surface charges essentially generate bound charges, though they generate a electric field, and we calculated the total electric field and used them in Gauss's law. In a similar picture, I want to understand what happens, what is the physical mechanism, what is the physical understanding of a magnetized uniformly magnetized medium. Now, so let me consider a uniformly magnetized medium. With magnetization M. So, what it implies is that the medium consists of small atomic dipoles, magnetic dipoles, and so let me try to represent these dipoles. So, I have let me take a medium like this, and so let me look at, I am looking at the top picture of the medium and I have atomic dipoles. So, let me assume that magnetization is pointing towards me. So, there are atomic dipoles like this. Highly magnified picture I am trying to draw here. So, these are all atomic currents, they are circulating currents, and each one of them is a small magnetic, tiny magnetic dipole. So, the material consists of a large number of these magnetic dipoles, and because it is uniformly magnetized, what you can see is at any point inside, for example, this point, you have a current flowing like this because of the upper loop and a current flowing in the reverse direction because of the lower loop, and the currents are equal. So, the net current at any point inside the medium is 0. At any point you see there is a current flowing clockwise and there is a current flowing in the reverse direction at the same point, with the net current being 0. So, in a uniformly magnetized medium, there seems to be no effective current within the medium, but look at the surface. At the surface there is a current flowing like this, there is a current flowing like this here, there is a current flowing like this here. So, this becomes equivalent to a current flowing in the outside in the surface like this. I am picturizing a uniformly magnetized medium. A uniformly magnetized medium means that there are tiny dipoles in the medium, and if the magnetization is pointing up, these tiny dipoles constitute current flowing like this in small loops, and it is uniformly magnetized medium. So, these currents are all equal, and at any point if you see here, there is a current flowing to the right and there is also a current flowing to the left because of the lower loop. So, the net current crossing this point is 0. Similarly, if you take any point within the medium, you will find that the net current passing through that point is 0. So, this cancellation is there within the volume of the medium, but at the surface, for example, on this surface you see that there is a current flowing like this here, there is another loop, there is a current flowing like this here, there is a current flowing like this here. So, this becomes effectively equivalent to current flowing on the surface. So, a uniformly magnetized medium is sort of equivalent to a medium in which there is a surface current flowing on the surface of the medium. So, let me try to relate this surface current, let me try to find out what is the surface current, what is the relationship of surface current to the magnetization. So, to do this we will take a cylindrical sample of area A and thickness T. Polarized, magnetized, uniformly magnetized along its axis. So, it is like this, something like this. So, magnetization is pointing up, this thickness is T and this area is A. So, let me draw the side picture. There is this medium here, this thickness is T and magnetization is pointing upwards, uniformly magnetized medium. So, I have a cylindrical sample uniformly magnetized parallel to the axis of the cylinder is vertical, of thickness T and cross sectional area A. Now, remember magnetization is the magnetic dipole moment per unit volume. This sample has a volume A times T. So, the magnetic dipole moment of the sample is equal to m times A times T. Magnetization is magnetic dipole moment per unit volume. So, magnetic dipole moment per unit volume into volume of the sample gives me the magnetic dipole moment of this sample. Now, I have just now shown you that a uniformly magnetized sample is equivalent to a current passing on the surface. So, this must be equal to, so if I have a uniformly magnetized sample like this, this must be equivalent to current going like this. Please remember, this is not an actual current which is flowing, this is not a conduction current, these are bound currents, these are currents generated by the bound electrons in the atom. So, let me recall here, these are currents which are current generated within the medium with a part of the atoms. It is not that one single electron is flowing like this or in the other direction, it is made up of tiny currents, and the net effect is to have a current on the surface of the sample. So, if I look at my problem which I am considering, this sample of radius A of thickness T is equivalent to a sample of thickness T and area A in which the current is flowing like this. Please remember, there will be loops like this, these loops are cancelling off everywhere inside the medium except on the surface. So, there seems to be a current flowing like this. So, I can write the magnetic moment also as current into area. The area of the sample is A, magnetization is like this. This is magnetization into volume is the magnetic dipole moment. The magnetized sample is equivalent to a surface current flowing like this. Magnetic dipole moment is also the current into the area, the current is flowing like this, area is in this direction here, and so I can equate these two quantities to find out m times a times t must be equal to I times a, and this gives me, this implies magnetization is equal to I by t. So, magnetization is nothing but current per unit length on the surface. Please note that this surface is perpendicular to magnetization. If you go back to the earlier picture here, this picture here there is no current in the upper and lower surfaces. The current is only on the side surface, because the currents are in this orientation, and if you can imagine, the current is actually the net effective current is flowing on the surface, and there is no effective current in the upper surface. So, please remember, the surface along which the equivalent current is flowing is perpendicular to magnetization here. So, magnetization is nothing but current per unit length. So, in this example of a magnetized sample which is magnetized like this is the magnetization here, and the effective current is like this, and this magnetization corresponds to a current per unit length of I by t. Now, this gives me a very nice way to imagine, to calculate to estimate the magnetic field of this, and let me go back and recall a solenoid. Solenoid having n turns per unit length and carrying current I. So, let me draw the solenoid here. So, we had considered this earlier. So, these are current carrying wire, current is going like this, and this is my z axis, and we had calculated the magnetic field. B is equal to mu naught n I k cap. Uniform magnetic field within the solenoid is inside and 0 outside. An infinitely long solenoid creates a uniform magnetic field within the solenoid of mu naught n I k cap. Outside the solenoid, the magnetic field is 0. We had calculated this. Now, this solenoid is assumed to be very closely wound. So, I can imagine as if the solenoid has a current going like this. These are wires carrying actual current. So, if you take a unit length, what will be the current per unit length? In a unit length, there will be n turns, each turn carrying a current I. So, current per unit length will be n I. Please note, if I take unit length of the solenoid, there will be n turns, each turn carrying a current I. So, the total current crossing a unit length in this direction is n times I. So, this n times I is nothing but current per unit length of the solenoid. So, the magnetic field produced by a solenoid is mu naught times current per unit length into k cap inside and 0 outside. Now, this gives me an idea that because a uniformly magnetized sample, suppose let me take a uniformly magnetized cylinder magnetized in this direction. This magnetized sample is equivalent to a current per unit length of m. So, comparing with a solenoid, this is very similar to a solenoid. In a solenoid, I had a current per unit length of Ni, produce a magnetic field which is mu naught times Ni into k cap. A uniformly magnetized cylinder, magnetized parallel to the axis, is equivalent to a solenoid, because both of them have a current passing along the surface. In a solenoid, the current per unit length is Ni. In a uniformly magnetized cylinder, the current per unit length is M. So, I can immediately write for the current, the magnetic field of a magnetized magnetic field of a uniformly magnetized cylinder, magnetized parallel to the axis, B is equal to mu naught times M times k cap, which is nothing but mu naught times M. Because M is along the k cap direction, M k cap is M vector. So, first of all, I have tried to show that a uniformly magnetized object is equivalent to a current on the surface. The current per unit length is simply magnetization. Please remember, the surface is perpendicular to magnetization I am considering. So, I have equated a magnetized sample to a surface current, and these currents, again let me emphasize, these currents are not conduction current, these are bound currents, these are currents which are bound to the atoms, each atom has its own current. It is like the bound charges in polarization, in the dielectric, these are bound currents. So, I first showed you that magnetization gives me a surface current, uniformly magnetized sample has a surface current. Then I showed that the surface current is actually nothing but magnetization. So, a uniformly magnetized sample has a surface current which is M on the surface, which is perpendicular to M vector. Then I am having an analogy of this problem with a solenoid, because for a solenoid I know the magnetic field. I know the magnetic field of a solenoid is given by this equation, and I can interpret this quantity N times I as nothing but the current per unit length, because if I take a unit length of the solenoid, in a unit length I have N turns and each turn carrying a current I. So, the current per unit length is N times I. So, all I need to do to calculate the magnetic field of a uniformly magnetized cylindrical sample, magnetized parallel to the axis, is I know that this is equivalent to a surface current of M, and that gives me a magnetic field which is B is equal to mu naught times M vector. So, this particular sample, this cylindrical sample which is magnetized parallel to the axis, creates a magnetic field mu naught M inside and is equal to 0 outside. I am assuming effectively an infinitely long magnetized sample. So, inside the sample the magnetic field is mu naught M, and outside the sample it is 0. Now, I can extend this argument to look at the following problem. I have a sample and I have wound wires on it. I have wound wires on a sample now. So, this is now a solenoid containing a medium inside now. So, this is the medium. So, I have a current flowing in like this and flowing out like this. So, solenoid N turns per unit length, carrying current I. Now, I wish to calculate what is the magnetic field inside. Now, this external magnetic field generated by the solenoid will magnetize the medium. That means, it will generate a magnetic dipole moment per unit volume inside the medium, and that magnetic dipole moment will be equivalent to a magnetization, and so let me call the magnetization M. the magnetic field is parallel to the axis. In the simplest example, the magnetization is also parallel to the axis. And so, what is the total magnetic field inside? P is equal to, now the magnetic field because of the conduction current is mu naught times Ni times k cap. The magnetic field due to the magnetization is mu naught m. Please note, there are two components of magnetic field now. The conduction current which is flowing in the wire is actually producing magnetic field mu naught Ni k inside. This magnetic field magnetizes the medium, which means it makes, we will come to more discussion of the properties of the media, magnetic properties of the media, but the magnetic field, external magnetic field will magnetize the medium just like an electric field polarizes the medium by polarizes the dielectric. An external magnetic field magnetizes the medium and I get a magnetization M. So, the total field is given by the sum of the field generated by the conduction current flowing in the wire and the magnetization. So, I can write this equation as B by mu naught minus M is equal to Ni k. Now, I introduce a new vector. We define H is equal to B by mu naught minus M. We define a new vector H vector which is B by mu naught minus M. So, I can substitute H vector into this equation and I get H is equal to Ni times k cap. Now, please remember H vector contains the properties of the medium through the magnetization, and on the right hand side there is no medium, there is no aspect of the medium at all on the right hand side. I have defined a new vector H vector which contains the medium property of M vector. So, I get a new form of Ampere's law which is integral H dot dl IF is equal to free current So, this is a new form of Ampere's law. We will discuss some examples with this, and this is very similar to modification of Gauss's law from electric field form to displacement current form, and this is a very interesting form of Ampere's law. We will discuss this a few examples and then discuss about magnetic properties of different kinds of materials. Thank you.